Hi, in this video we're going to look at trying to understand moles and formula weight. And so once you're done with this video and the accompanying activities, you should be able to define and use the idea of moles as it's used in chemistry, interconvert between moles and mass for elements and compounds. So let's consider a reaction that we've seen before. It's the reaction of methane and oxygen reacting to form carbon dioxide and water. And we've shown this in terms of showing the molecules themselves, and we see that one molecule of methane should react with 2 molecules of oxygen to form 1 molecule of CO2 and 2 molecules of water. But the reality is, if we were trying to do this in a lab, well, molecules and atoms are really small. We can't practically actually deal with single molecules. It's just impossible. If we actually tried to weigh the molecules, turns out 1 molecule of methane weighs 2.65 times 10 to the negative 23rd grams, so that's 0.0000000, whole bunch of zeros, 265 grams. And if we had a really good lab scale, we could actually probably get down to 0.00001 grams. And so we can't actually put these things on balance. We can't measure them. Again, they're just really too small. The way that we deal with that is a unit called the mole in chemistry. And a mole is really just a counting unit. And you may be familiar with some counting units. Probably you're familiar with a dozen, right? Most likely you know that's 12 things. A score is a little bit less common, but thanks to a famous speech by Abraham Lincoln, many people know that a score is 20. Even less common is a gross, but it's a dozen, or 144 of items. And so you know a couple of these, and you may actually use them on a moderately regular basis. Well, to be perfectly honest, the mole is the same, but it's just much, much bigger. So it's 6.022 times 10 to the 23 items, and if you have that many items, you have a mole of that item. And this is known as Avogadro's number, so you might be familiar with that. It's something that's actually empirically determined, and it's very commonly used in chemistry. And here we can see some different samples of 1 mole. And so we can see a block of aluminum, copper, and carbon, and you can see that relative to the quarter just to give a little bit of sense of scale there. And what we see here is if we look at the weights, each of these weights are different, but the thing that's common across all of them is the number of atoms that are present. So each of those have the same number of atoms. If we had a mole of water, then that's about a tablespoon of water, just to give you a little bit of sense of that. Now, converting between a number of items and moles, well, my guess is you can do that, right? How many items are in a dozen? You're probably pretty quick in your head to think, okay, 12. What if we make it a little harder? How many are in 3 dozen? Probably you got 36 pretty quick. But how did you figure that out? Well, I'm going to go out on a limb and say you probably multiplied that. Maybe you added 12 plus 12 plus 12, but most likely you took 3 dozen items and you multiplied that by 12. In your head, you probably didn't sort of formalize this, but essentially this is what you did. You took 3 dozen items, you said, oh, I know I've got 12 items per 1 dozen, and so I'll multiply those things together and I get 36 items. And if we do this mathematically and we pay attention, these units would even cancel out, and so everything works really well. Now we could have done that in the opposite direction, right? We could have said, oh, if you had 36 items, how many dozen do you have? And you would have been able to do that as well, right? But you know now I need to divide by 12 because there's fewer dozens than there are items. And so we would do that same thing, and again, our units could cancel out here. And so that actually works out really nicely. Now, the mole works the exact same way, as it turns out. But instead of having 12 items, we have 6.022 times 10 to the 23rd items. So if we have that many items, that's 1 mole of those items. Now, obviously, for things like flashlights or pencils or whatever, this isn't a number that's ever going to make sense. It's going to be about as big as the entire world. So instead, we pretty much talk about these in terms of molecules, atoms, photons, other things that are on that atomic size. And Avogadro's number then allows us to really be able to convert between the number of moles of something that we have and the number of individual items. And the mole is abbreviated as an MOL. Now, there's a couple different ways that you might see these and use these. So just like we were able to take that 12 items per 1 dozen up here, we can either use it with that Avogadro's number on the top and divide by the number of moles, or vice versa. So we can always flip these unit conversions around. Now, one way that we'll often represent this in this class is going to be showing sort of a schematic of this. Here we have number of molecules, we want to convert over to moles, and so Avogadro's number is going to allow us to be able to interconvert between those two things. And we're going to use that representation a little bit more. Now, how does this actually relate to reactions? Well, from the previous activity that you've done, you've seen that a balanced equation basically tells us how many things react together. So here we've got hydrogen plus oxygen giving us water. And so that balanced equation is essentially our recipe. But we know that multiples of that recipe also work. right? I can have 2 hydrogens with 1 water, or I could have 4 hydrogens with 2 waters, as is depicted here. And both of those will completely react. But it turns out that any multiple is still valid, and that includes 6.02 times 10 to the 23rd times, so a mole's worth of times. So we could also say then that 2 moles of H2 reacts with 1 mole of O2 to form 2 moles of water. And so we can also do that. So now let's see if we can carry this just a little bit further. Now, it turns out this idea of a mole is extremely useful. If we have 1 hydrogen atom, it turns out that weighs 1.008 atomic mass units. If we have a mole's worth of atoms, hydrogen atoms, that also weighs 1.008, but now the unit is grams. And so the conversion between atomic mass units and grams is Avogadro's number yet again. And so here we have a couple different atoms, we have a couple different molecules that we're showing the weights of. So how do we actually get some of these? Well, we actually go to the periodic table in order to find these. So if we look on the periodic table, we have masses of each of these individual pieces. And so here we can see hydrogen is 1.008, we can see oxygen is 15.999. And so if we then want to know the mass of H2O, well, that says I need 2 times the mass of hydrogen plus 1 times the mass of oxygen. And so in order to do that, I'm going to say, cool, so 2 times this 1.008 that we have up here, plus 1 mole of the mass of oxygen, so multiply those together. If we cancel everything out, what we end up finding is that we get our units of grams, we get 18.015 grams, and that's for 1 mole of water. So let's see if we can use that value for a moment. We might be faced with a question such as, how many moles are in 100 grams of water? Well, we know that that formula can allow us to interconvert between moles and mass, and we can go either way, so we can go from mass to moles. And so since we know the mass, we could set up an equation where we take that mass, we multiply it by the formula weight with the denominator being in grams. That will allow the units to cancel here and leave us in units of moles. And when we do that, we should get 5.551 moles of water. So now we've answered that question of how many moles of water are in 100 grams. And so this becomes part of essentially your calculation toolkit. And so we've shown a couple different pieces here. One, we've shown how to interconvert between items and moles, and we use Avogadro's number to do that. Or we can interconvert between moles and mass using formula weight. And so these are going to be tools that you always have at your disposal whenever you're approaching any sort of chemical reaction that you have to address quantitatively. Of course, you might notice that moles appear in both of these, so we do have the ability to potentially combine these things together to start to build up bigger and longer chains in order to be able to address these things. And so these calculations can actually be combined to then solve much more complex problems. And so you'll have the opportunity to do that, and we'll also begin to add in more tools as we go forward.